Hey there, Mr. Sutton here with the BC Calculus 7-9 Part 2 homework solutions on integral and p-series tests. For this problem, we're given three series and we're asked which of these converge. So we're just going to go through each of them and test them. For this first one, this is actually a p-series. This is n times n to the 1/2 or n to the 3/2. So we have a p-series with p equals 3/2. Since this is greater than 1, that means that this series is going to converge by the p-series test. All right, this next one, this is a geometric series. We have a common ratio of 1/3. Since this is absolute value less than 1, that means we're going to converge by the geometric series test. And then there's this last one. So right now it's really down to 1 and 2 or 1, 2, and 3. This is going to decide everything here. So for this one, we're actually going to have to use the integral test. Now, to make sure that we can, we notice that for n values greater than or equal to 2, this 1 over n ln of n function is continuous. At least past 2 it is. At 0 and 1 we have some discontinuities, but 2 and onwards we're fine. It's also positive. There's no negatives at all in here. And we're decreasing. Our denominator is getting bigger as we get larger and larger n values. Since this is continuous, positive, and decreasing on this interval, we go ahead and we use the integral test. So let's take the integral of this thing. It's going to be an improper integral. So we're going to have limit as n approaches infinity of, let's see, this is going to be 2 to b. Actually, limit as b approaches infinity, 2 to b of all this stuff inside an integral. So I'm going to have to use substitution on this one. ln is kind of an inner function whose derivative, 1 over n, is in here. So let me let my u value be ln of n. So that means then du equals 1 over n dn. And then I can write n du is equal to dn. So I'll do these substitutions in a minute, but I also have to swap out my limits of integration here, because this is a definite integral. So if u equals 2, or n equals 2 rather, u is going to be ln of 2. And then if n equals b, that means u is going to be ln of b. So swapping it all out, I have the limit as b approaches infinity of, now we're going from ln of 2 to ln of b. And instead of dn, I've got n du. And instead of ln of n, I'm swapping that out for u. So 4 places I make substitutions. Cleaning this up a little bit, these n's are going to cancel, so I just have du over u. And now I can go ahead and take my antiderivative with respect to u. So this is going to be, in my evaluation box now, ln absolute value of u from ln of 2 to ln of b. Still have that limit of b approaching infinity sticking around, though. So I can write this now as ln of b minus ln of 2. And I'm going to leave the absolute value around just in case there's some weird kind of negative thing happening when I take the ln of this number. And then let's go ahead now and take the limit as b approaches infinity. So nothing's happening over here with this ln of 2, but as b approaches infinity, this ln of b goes to infinity. So you're taking another ln of infinity, which also is going to infinity. So this is overall going to infinity. Since this integral diverges, that means its corresponding series up here is also going to diverge by the integral test. So at the end of the day, only options 1 and 2 converged, giving us answer choice D. For number 7, we want to know all values of p for which the integral from 1 to infinity of 1 over x to the 2 p dx converges. Well, if we're talking about converging, we're talking about series. So the easiest way to do this one is to turn it into a series question. We know by the integral test that if this converges, or this is going to converge wherever the series of 1 over n to the 2p from 1 to infinity converges. So if we can figure out where this series converges, we've figured out where the integral converges, because they're basically one and the same thing when it comes to whether or not they converge. So by the p-series test now, looking at this series, we know that in general, when this exponent is greater than 1, the series converges. So by the p-series test then, this series will converge where 2p, which is this whole exponent, is greater than 1, which means it's going to converge when p is greater than 1/2. So that's going to be answer choice C. For this one, we want to know for what values of p will these two series converge. So we'll take them one at a time here. This first one is actually a p series, and our p value, and I put p in quotation marks, is actually this 2p term here. It's that exponent. So this is going to converge wherever 2p is greater than 1, which is to say the p value in this problem has to be greater than 1/2. All right. So for this next one here, this is a geometric series. We have repeated multiplication. The r value in this case is p over 2. And this will converge wherever the absolute value of r, which is p over 2, ends up being less than 1. So this means that we can multiply by 2 here. And then we can say that p is going to be between -2 and +2. So now we have to write our final interval of convergence for p. So the lowest value, or the highest value, the highest lower value, I should say, that we're going to converge at the border is going to be this 1/2. We have to be greater than 1/2. So this -2 to 1/2 stuff we don't care about because you have to be at least 1/2 for p to make this converge. And then the highest we can go is 2, so we'll say less than 2. And that's going to be answer choice C. For this problem, we want to know what value of p makes the integral from 1 to infinity of 1 over x to the p diverge, and also the integral from 0 to 1 of that same thing. All right, so we've got two different situations going on here. We have basically an infinite improper integral, and then we have this other improper integral because we have 0 making this undefined if you plug it in. So what value of p is going to make both of these mess up? Well, let's start with the low-hanging fruit, which is this infinite series. So we know this thing by the integral test. This thing is going to have the same behavior as a p series of 1 over n to the p, basically. So since we have essentially a p series, we know this is going to diverge whenever this p value is less than or equal to 1. Well, that means we're going to eliminate answer choice A, but we're still stuck with answer choices B through E. So we now have to tackle this integral here. Now this integral doesn't really have any connection to a series. This is just a straight up improper integral that we have to evaluate. So let's do that, and p is a constant that's just going to kind of stick around as we go, and we're going to have to analyze it in the end. So since this is going to be undefined when I plug 0 in for x, I need to rewrite this as a limit as a approaches 0 from the right of the integral from a to 1 of 1 over x to the p dx. So just basically making this a little bit more legal to write. And now let me go ahead and take my antiderivative. Before I do that, though, let me make this x to the negative p. Just make it a little bit easier to anti-differentiate. And now using my reverse power rule, this exponent bumps up to negative p plus 1, or 1 minus p. Dividing by that, I've got x to the 1 minus p over 1 minus p, evaluated from a to 1. And plug in all this in. If I plug in 1 for x, I essentially just have 1 over 1 minus p for that first term. And now I'm going to plug in all this stuff with a instead of x. And now just analyzing what's happening here. As a approaches 0, it's going to make a difference what kind of value p is. If p is a number that's bigger than 1, that's going to give me a negative exponent, which is going to move a to the denominator, and will essentially be dividing by 0 if a ends up in the denominator. So we're going to diverge if p is greater than 1 and a is approaching 0. Now, if we take a look at other p-values that might mess this up, if p is exactly 1, well, that's going to give us 0 in the denominator anyway for any a value. And if p is less than 1, well, nothing bad happens there because then a stays in the numerator, and that would just zero out the second term. All right, so we see here that p greater than or equal to 1 is going to mess up this integral. So we have two conditions we have to meet. We need a p-value that is less than or equal to 1, and also a p-value that is greater than or equal to 1 at the same time. Well, the only way to be less than or equal to 1 and greater than or equal to 1 is if you're exactly 1. So that's going to give us answer choice B. On this problem, we want to know which of these three options converges. So we'll just go through one by one and see what we can eliminate. For this first one, if you look at the general term here, this is a p-series with a p-value of 2. Since that's greater than 1, that means that this series is going to converge by the p-series test. On this next one, we have a general term of 1 over n. That we recognize as the harmonic series, which we know automatically is going to diverge. And this last one, there's a few ways to do this one. If you know about alternating series test, this one is alternating and decreasing an absolute value to 0. So AST would prove that this converges. But another way to do this one, if you haven't seen that test yet, is you might notice that we're multiplying by negative 1/3 each time to get the next term. So this is actually a geometric series with an absolute value of the common ratio that's 1/3. Since that absolute value of the ratio is less than 1, that means that this is going to converge by the geometric series test. So at the end, options 1 and 3 were the only ones that converged, so choice C. For this problem, we want to know for what p-value this integral converges. Since we have an infinite integral, and this function is actually a continuous, positive, and decreasing on the interval from 1 to infinity, that means that by the integral test, this will converge if the summation of 1 over n to the 3p plus 1 converges. And again, that's by the integral test. So we need to figure out the convergence of this series. Well, this is actually a p-series, and this means that we have a p-value of 3p plus 1. So by the p-series test, this will converge if 3p plus 1 has a value that's greater than 1. So let's go ahead and solve for p in this situation. If we subtract 1, we've got 0. Divide by 3, we still have 0. So if p is greater than 0, then this summation, this series will converge, which will make this integral converge as well. So that's going to be choice C. On this problem, we want to know which of these 3 series converge, and it doesn't look like there's an answer choice for all of them converging, so at least one of them diverges. So quickly applying the nth term test to see if any of these just fail outright, we see that the first limit goes to 0, the next limit goes to 0 because n factorial grows faster than 3 to the n, and this last one, e is smaller than pi, so this is also going to 0 if we multiply over and over by that. So we're going to have to use some more specific tests. For this first one, this is actually a p-series. This is really n to the 1/2 power downstairs, so we have a p-value of 1/2. Since 1/2 is less than or equal to 1, that means this diverges by the p-series test. For this next one, we're going to have to really get to the bottom of this one, we're going to need the ratio test. Whenever you see exponentials and factorials, ratio test is a good one. So I have my n plus 1th term, 3 to the n plus 1 over n plus 1 factorial, divided by the nth term. Same change flip, I've got 3 to the n plus 1 and n factorial in the numerator, and I've got 3 to the n and n plus 1 factorial in the denominator. So these 3's cancel, leaving me with just a 3 upstairs if I subtract those exponents. These factorials also cancel, leaving me with just n plus 1 in the denominator. So I have the limit as n approaches infinity of this, and I guess I could leave it an absolute value, but I know at this point that this is going to come out to a positive number if n is all numbers 1 and larger. So this is going to go to infinity, or 0 rather. As n goes to infinity, this fraction goes to 0 because we have a bottom-heavy function. 0 is less than 1. So the ratio test unambiguously tells us that we're going to be converging on this one. Okay, for this next one, this is actually a geometric series. We have a common ratio whose absolute value is e over pi. Since e is smaller than pi, this is a number that is less than 1, which means by the geometric series test, option 3 is going to converge. So it's options 2 and 3 that converge. Always look to see what they want. So that's going to be choice E. On this problem, we want to know which of these 3 series diverges, so be careful there. It's reversed from what they usually want. So we'll take a look at all these with the nth term test, and then we'll try some other test if that doesn't work. So for this first one, sine of 2, I know that's going to be at most 1. I don't really know what the exact value is, but we have 1 over pi, or something less than 1 over pi, being raised to the nth power. That's going to go to 0 for the nth term test. So I move on to another test, geometric test. This is actually a geometric series with an r value of sine of 2 over pi, because we're multiplying by that over and over again. Now, again, this is going to be less than at most 1 over pi, because sine doesn't get any higher than 1. And 1 over pi, most importantly, is less than 1. So this one actually converges, and it's not going to be in our answer. So anything that has a 1 in it, such as B, C, or E, can be eliminated right away. So now it's down to A or D. So we actually know for certain that choice 3 here is going to diverge just because it's in both of our remaining answer choices. So it really comes down to answer choice or option 2 here. This one also goes to 0 if you try the nth term test, but you might notice this is actually a p-series. We have really n to the 1/3 power downstairs, and 1/3 is less than 1, which means that this thing is going to diverge. Anything less than or equal to 1 is going to diverge for a p-series. All right, so definitely 2 works. So probably answer choice D, but let's just look at 3 to be sure. Now this one, using my nth term test, as n approaches infinity, this 1 goes away. You just have e to the n over itself, which is just 1. Since the limit does not give us 0 of that nth term, that means that this is going to diverge as well by the nth term test. So definitely choice D then.